In this module, we overview different types of spectroscopy. Photon-assisted transitions are fundamental to understanding the behavior of atoms and molecules in spectroscopy. These transitions involve the absorption or emission of electromagnetic radiation, leading to changes between allowed quantum states of the system. There are three primary processes to be aware of. They are illustrated in this figure. Here, the red filled circles indicate the initial and the orange filled circles represent the final energy levels. Absorption. Here, an incident photon is absorbed by the atom or molecule, causing an electron to transition to a higher energy level. Spontaneous emission. This is a random event where an excited state relaxes to a lower energy state, emitting a photon in the process. The emitted photons are incoherent, meaning their phases are random. Stimulated emission. Initiated by an incident photon, this process results in the emission of a photon that has the same phase and direction of propagation as the incident photon. This coherent photon emission is the principle behind lasers, which produce a beam with minimal divergence. The existing spectroscopy types can be classified based on the type of the photon-molecule interactions. In absorption spectroscopy, the net absorption of radiation is monitored across a range of frequencies as it passes through a sample. It's essential to understand that while radiation can be absorbed, it can also stimulate the emission of radiation. Hence, what we detect is the net absorption. Some common types of absorption spectroscopy include UV visible absorption spectroscopy and infrared IR absorption spectroscopy. On the other hand, emission spectroscopy focuses on detecting and analyzing the electromagnetic radiation emitted when molecules transition from a higher to a lower energy state. Fluorescence spectroscopy and phosphorescence spectroscopy are prime examples of emission spectroscopy. In principle, both absorption and emission spectroscopy provide insights into the electronic, vibrational, or rotational energy levels of molecules. However, the choice between these techniques often depends on practical considerations and the specific information sought. Among different spectroscopy techniques, we also distinguish between atomic and molecular spectroscopies. Atomic spectroscopy methods focus on the study of electromagnetic radiation absorbed and emitted by atoms. When we talk about atomic spectroscopy, we are primarily dealing with individual atoms, often vaporized and atomized to facilitate the study. Each element has its unique spectral signature, allowing us to pinpoint specific elemental compositions within a sample. These methods may reveal not only the number and type of atoms present, but also their ionization states and, in some cases, how they might be bonded. The molecular spectroscopy branch of spectroscopic techniques is concerned with the interaction of electromagnetic radiation with molecules. Unlike atomic spectroscopy, which deals with individual atoms, molecular spectroscopy examines the transitions in electronic, vibrational, or rotational energy levels within a molecule. It provides valuable insights into molecular structure, chemical composition, and even the dynamics of molecular interactions. Now we will show a representation of the energy levels in a chemical system. The vertical axis represents the energy, and as we move upwards, the energy increases. At the broadest level, we have energy levels corresponding to different electronic states. They are represented by the blue lines labeled E0, E1, and so on. The transitions between them involve changes in the electronic configuration of the molecule. They correspond to the largest energy differences. Specifically, the separation between electronic energy levels typically ranges from about 100 to 1000 kilojoule per mole. The transitions between different electronic states are addressed by electronic spectroscopy. A change of electronic configuration is the only type of change that one can expect for an isolated atom or an ion. Respectively, electronic spectroscopy is the only type of spectroscopy that makes sense for them. In molecular spectroscopy, the energy levels of a molecule are more elaborated than those of an isolated atom. This complexity arises because, in addition to electronic transitions, molecules can undergo changes in their rotational and vibrational states. Let us investigate these energy states and outline the hierarchy of energy levels. Within each electronic state, we have vibrational energy levels depicted in red. The transitions between them involve changes in the bond lengths and angles of the molecule. The energy differences for vibrational transitions are smaller than for electronic transitions, typically around 10 to 100 kilojoule per mole. The types of spectroscopy that address transitions between vibrational states belong to the family of vibrational spectroscopy methods. Nested within each vibrational level are the rotational energy levels. These transitions involve changes in the molecule's rotation around its center of mass. The energy differences for rotational transitions are the smallest, often as small as 10 to 100 joule per mole. To summarize, the hierarchy of energy levels in a molecule from the largest to the smallest energy differences goes from electronic to vibrational to rotational. Each type of transition provides unique insight into the molecule's structure and behavior, making spectroscopy a powerful tool for understanding molecular systems. The electromagnetic spectrum encompasses a vast range of energy, from the highest energy gamma rays to the lowest energy radio waves. Different segments of this spectrum interact with matter in unique ways, leading to various spectroscopic techniques. It's crucial to understand that specific energy differences associated with specific processes in chemical systems correspond to specific photon energies, which in turn translate to specific wavelength ranges. Let's visualize this spectrum in descending order of energy. Gamma rays have the highest energy and shortest wavelengths and are typically produced by the radioactive decay of atomic nuclei. As a penetrating and ionizing form of electromagnetic radiation, gamma rays cause damage at a cellular level. They are not used in spectroscopy methods utilized by chemists. A somewhat less energetic form of electromagnetic radiation is known as X-rays. The energy of X-ray photons corresponds to the energy differences for changes in the electronic configuration of the innermost electrons of an atom, known as core electrons. The spectra obtained using X-ray are atom-specific, allowing for elemental detection. An example of a spectroscopic technique operating in this range is X-ray absorption spectroscopy. Ultraviolet radiation and visible light regions are primarily associated with electronic spectroscopy involving valence electrons. These techniques address electronic transitions within molecules, giving insights into molecular structures and dynamics. Infrared radiation provides information on the vibrational modes of molecules, as exemplified by infrared absorption spectroscopy. The microwave region is predominantly associated with rotational spectroscopy, revealing information about the rotation of molecules. Finally, radio waves are employed in nuclear magnetic resonance spectroscopy, which studies the nuclear environments of atoms within molecules.